Okay, so thank you very much, everyone, for joining in this weekly research seminar. My name is Muhammad Haris, and today we have Dr. Karthik Nandakumar, who will present his work titled Security, Privacy, and Trustworthiness in the AI World. Karthik Nandakumar is an associate professor in the Computer Vision Department at Mohammed bin Zayed University of Artificial Intelligence. Prior to joining MBZUAI, he was a research staff member at IBM Research Singapore and a scientist at Institute for Infocom Research, A-Star, Singapore. His primary interests include computer vision, machine learning, biometric recognition, and applied cryptography. Specifically, he's interested in research on deep learning algorithms for biometrics and video surveillance applications, as well as security, privacy, and trust-related issues in artificial intelligence. He's a senior area editor for IEEE Transactions on Information Forensic and Security, and a distinguished industry speaker for IEEE Signal Processing Society. So if you have any questions during the talk, you can always type in the QA tab, or you can ask at the end of the talk. So, Dr. Karthik, the stage is all yours. Thank you.
Thank you, Dr. Harris, for the kind introduction. And hello, everyone. As Dr. Harris mentioned, I'm Karthik Nandakumar. I'm an associate professor in the computer vision department at MBZUAI. So today, I'll focus mainly on my research work in the area of security, privacy, and trustworthiness in the AI systems in general. So there will be three parts in my talk. First part, I'll just cover the general vulnerabilities of machine learning systems to different kinds of attacks. So then I'll focus on a specific solution which we have developed, which is how do you do machine learning on encrypted data so that it addresses some of the privacy and security issues. And towards the end of my talk, I'll also briefly introduce my work in the area of federated learning, where we are trying to develop more robust federated or decentralized learning algorithms, which work even in the presence of malicious users. Okay, to begin with, I'll just briefly describe some of the security vulnerabilities in machine learning systems. As you all know, this is the general model of any machine learning system. You have a physical world, and you have data coming from the physical world, which is captured as a digital form using some kind of sensor. So this could be cameras, in the case of computer vision, speech, or some kind of text processors. Right? So all this gives you digital representation of the input. And basically, there are two steps in a machine learning process. One is the learning algorithm, which takes the training data and then comes up with a machine learning model that fits this data. And this model is stored in somewhere, in some database or in some location. And whenever you want to make predictions on some input data, you take the stored model and apply this inference algorithm, which will give you a predicted value or output. So this general machine learning system is vulnerable to a number of attacks. So here I'm kind of highlighting 8 different kinds of attacks. So the first kind of attack is physical spoofs. So one way to fool a machine learning system is basically go and manipulate the input to the system. For example, let's say if you have a stop sign on a road, can I do some manipulation to the stop sign so that the stop sign is never detected by an autonomous vehicle, right? So these kind of manipulations on the physical world are called physical spoofs. So next kind of attack, we have what is known as data poisoning kind of attacks, where the goal is, let's say during the training process, the training data is kind of poisoned or manipulated or tampered with in such a way that the algorithm learns the wrong things. So if let's say I am an adversary, I want to fool this machine learning system, I can poison the data in such a way that whenever I give a particular input, the algorithm will output the desired output that I want. Right? So you can poison the learning algorithm in this way. So that is the second kind of attack. Third, you have this model tampering. So let's say I don't do any poisoning on the training data itself, but after the model is learned, then I can go and tamper with the model so that the inference doesn't work properly. Then we have a bunch of attacks which are all targeted at the stored model. So these include membership inference attack, model inversion, and model extraction attacks. So I will explain these attacks in detail later. And finally, we have these two main classes of attacks, which are very well known in the machine learning and computer vision literature. So one is known as adversarial samples, where the goal is, can I make some small modifications to the input so that my inference algorithm gets fooled and it predicts the wrong output. So those kind of modified samples are called adversarial samples. And finally, we have this breach of confidentiality, which means, let's say you're giving out some data for training or inference. What is the likelihood that this data will not be abused for some other purpose? Right? So you can use the same data and then do something else with it, which you are not supposed to do. So that constitutes a breach of confidentiality. So these attacks can be broadly classified into three different groups. So, and these cause different kinds of threats to the machine learning system. So the first threat is integrity. So integrity means anything which tampers with the normal operation of a machine learning system. So that is called as an integrity threat. So for example, this attacks 1, 2, 3, and 7 are mainly um, targeted at reducing the integrity of the system. The second kind of attack is availability, right? So this data poisoning as well as model tampering can also prevent you from using the system. So let's say I'm a genuine user who wants to use this machine learning system. The attacker can make some changes to the learning algorithm or the inference algorithm or the model and make the system unusable to a genuine users. So that is basically an availability threat. And then there's third class of threat, which is related to privacy and confidentiality of the data. So if the confidentiality of the data is revealed, then it basically affects the privacy of the individuals who are the users providing this data. Right. So my main research goal is to develop secure, privacy-preserving, and trustworthy machine learning algorithms and AI systems that can handle these kind of attacks. Okay, so before I proceed further on explaining some of these attacks, I'd like to introduce the concept of machine learning as a service. Right, so this concept is becoming very popular today. So what are the things or what are the ingredients you need for a machine learning system? So you have people, you have data generated from these people, you have models, machine learning models built upon this data, and then you need the computing resources to build the model and to run the model. So all these constitute what is known as the AI marketplace. And as AI becomes more widespread in today's world, now this marketplace is kind of getting fragmented. Especially there are two types of people. So there are business users who have data. All they want to do is just find a fast and accurate machine learning model that works on their data. Right? So they don't care about how the model is built and all that. And then there's other group of people, the data scientists, who just want to build the next big machine learning model. Right? So they don't care about how this model is applied in a real world application. So their goal is, okay, you give me the data and then I'll build a model. So they don't really care about how the model is being used in the real world. So because of this dichotomy, so what really happens is we have a kind of a machine learning as a service paradigm emerging, where you have business users. These users have data which can be used for training or inference, and then you have these machine learning service providers, which includes big companies such as Google, Amazon, and so on, and also many um, startups which are working in this area, right? So let's say I'm a hospital or a bank and I'm a business user in this organization. I don't need to build a machine learning team or AI team within my organization in order to make use of the data. So I can just outsource my data to this learning service provider uh, to, to build a machine learning model or or the other way, so you can actually do the training part, or you can also do the inference. So for example, you already have a model. Instead of running it locally, you basically provide it to this learning service provider. They will just run the inference for you. So you, anytime you provide the input data, they will give you a prediction. So, and this is done through standard application programmer interfaces, APIs. Right? So you have this dichotomy between these business users and the learning service providers. And many of these attacks, which I described in the previous slide, like the model inversion, model extraction, membership inference, and so on, are more applicable in the case of this machine learning as a service paradigm. So if, let's say you are an organization where you own the data, you build the model and you run the model, then the possibility of such a system being attacked is very less. Whereas if you have the data in one place, if you have the model and the computational resources in a different place, and then you want to send data, receive outputs, and so on, that's where you introduce a lot of attack surfaces. Okay, so now let's see some of the very popular attacks on machine learning systems. As I mentioned, the first kind of attack is a physical spoof. So here I have shown you some images on the left, so which are provided as input to a face recognition system. So please think about which of these images are real. By real, I mean these images are captured from a live person standing in front of the camera. So it turns out that all these images are fake in the sense, so there is no live person standing in front of the camera. So the first column is you show a printed photo in front of the camera. The second column is you flash an iPhone or an iPad. Second and third columns stand for iPhone and the iPad. So you put a face image of a person on an iPhone and then flash it in front of the camera. So all these are fake images, but for a human eye, they look very um, close to real images, right? And the converse is also true. So you have, so these are several images of the same person. The question is, which of these images are fake, that is not coming from a live person? It turns out that all of these images are real, although there are large number of variations in these images. So this is one type of physical spoof where it is usually very difficult for the human eye to detect whether this is a spoof or a real image. On the other hand, if you are able to train a machine learning model to classify these two kinds of images, the real versus fake, such algorithms seem to work quite well. So this is a kind of spoof where it's difficult for the human eye, but it's very difficult for a machine learning algorithm. Sorry, very easy for a machine learning algorithm. On the other hand, we also have a different kind of attack. So for example, we have this disappearance kind of attack. So let's say you have developed a computer vision system to detect stop signs on an autonomous vehicle. So, but just by modifying the stop sign by putting a poster on top of it or sticking something on top of it, I can make it disappear from the object detector. So let's say this object detector running on this vehicle, if it looks at this image, it will not detect a stop sign. So this is called as a disappearance attack. And the opposite is also true. So I can create some random images which will which I can throw in front of this camera, and then the system will detect that this is a stop sign. So this is called as a creation attack. So here, these kind of attacks are very easy to detect visually. So if you show this to a human, the human can always say that, okay, the left two images are stop sign and the right image is some random image and it's not a stop sign. But it turns out that it is very difficult for machine learning systems or machine learning algorithms to detect these kind of attacks. So you have physical spoofs which are sometimes imperceptible to the human eye, but machine learning systems can easily detect them. And then you have spoofs which are actually easily detectable by the human eye, but very difficult for machine learning systems to detect. So you have both ends of the spectrum. Next class of attack is basically an adversarial attack. So in 2014, some researchers from Google came up with this kind of attack, especially it's an encrypting property of some of the neural networks. So what they basically did is take any image, I can add some noise pattern in the image so that the classification algorithm will always give me ostrich as the output class, right? So if I take this um, noise image in the middle, if I add it to the original image, the school bus on the left, and I pass it through the classifier, it will give me the classifier output as ostrich. Right? So this is a kind of a targeted attack, and this one is data dependent. So for every kind of image, I can come up with some data dependent noise, which will make it turn into a different class. So this is one kind of problem in machine learning systems. Then there is also this other class, which is universal adversarial perturbation. So the idea here is, okay, I don't want to generate data dependent noise. Can I come up with a universal noise pattern, which when added to any image is very likely to flip its label, right? So here you have this noise pattern in the middle, which is kind of universal. So if I take this noise pattern and add it to any of these images on the left, and then this blue things are the true classes of these images. So once I add this image and pass through the machine learning classifier, my output labels get flipped. So they give me a wrong output label. So even though the image itself is not changing much, the output label becomes wrong most of the time. So in this case, 8 out of 9 cases is written the wrong result. So both these kind of adversarial attacks are possible. I am specifically interested in adversarial attacks on medical imaging or healthcare related systems. So here also the same kind of attacks are feasible. For example, recently people have shown that you can take these adversarial perturbations and add it to different kinds of medical images, like the diabetic retinopathy image or the chest X-ray or the skin lesion images, which are used for skin cancer detection. And then once you add these perturbations, you can change it, change the class label from having no disease to having a disease, or from not, or from disease to non-disease, and so on. Right? You can flip the label anywhere, anyhow. You can flip the label, and in particular, these kind of attacks on medical images are more vulnerable to universal adversarial perturbations. For example, in this recent paper, Hirano et al. Have shown that irrespective of what kind of machine learning model you use. So here is some of the most famous convolutional neural network architectures, such as Inception, the VGG, WestNet, GamesNet, and so on. Right. So all these model architectures are vulnerable to these kind of attacks, and this is also agnostic to the imaging type. Right. So I can come up with adversarial perturbations that work across imaging types. Um, doesn't matter whether it is skin lesion images or OCT images or chest X-ray images. So I can add these perturbations to any of these image classes, and then I can fool the system. And then the third thing is it is also agnostic to constraint on the noise. So here P equals to 2 and P equals to infinity refers to the norm of the noise, right? So in the case of P equal to 2, you are basically saying that the average noise which is added to each of these pixels should be less than the threshold. Whereas in the P equals infinity case, you are saying the maximum amount of noise that we can add to a specific pixel is constrained, right? Irrespective of how you add the noise, you can show that most of these model architectures across different image classes and across different kinds of noise patterns, they, they get very fooled very easily. The numbers in this table represent the fooling rates for these universal adversarial perturbations. And the numbers in the parentheses indicate the rate at which the label gets flipped if you just add some random noise. So if instead of adding a specific kind of universal adversarial perturbation, if I just add some random noise to the image, then they get fooled only very less number of times, as shown in the numbers in the parentheses in this table. On the other hand, if I choose the perturbation in such a way that it is adversarial, then most of these systems are fooled most of the times. So this gives us the intuition, right? So many of the researchers have been working on how to detect these kind of adversarial attacks. But most of them, they kind of assume, okay, this is my model and this is my image domain, and this is the kind of noise pattern which I'm going to use. And then they try to come up with a defense mechanism against specific architectures, specific image type, and specific noise patterns. On the other hand, it seems that this kind of vulnerability is universal in the sense that it spreads across model architecture, imaging type, and constraint and noise. So the challenge really is how do you build the defense mechanism that doesn't care about the model architecture, irrespective of the model architecture, imaging type, or the noise constraints. It can still detect these adversarial samples. So that is one of the open challenges in adversarial machine learning. Next, we have these few classes of attacks, the three classes, namely membership inference, model inversion, model extraction, and all of them are working in the machine learning as a service scenario. So the first attack is membership inference. The idea is very simple. So let's say there's a black box model which is available with the service provider, and I want to know whether my training data is part of this, my records are part of the training data used for training this classifier, right? So that's the goal here. So you are given a machine learning model and you have a record, and you want to determine whether this data point or record was used as part of the model's training set. So this kind of attack might look very innocuous, right? Not um, not a big deal. So what are you going to do by knowing whether your data is there in the training set or not? But it turns out that this is essentially a problem of this classifier overfitting itself to the training data. So what really happens is by repeatedly querying this classifier, I can actually find out the complete training data that was used to train this model. And that is a significant privacy, that has significant privacy implications. Next, we have this model inversion attack where the goal is you are given an output from a target model, and then using just this output, can we reconstruct back the private input that was used to generate this output? So let's say I have a face image and I pass through some target model, I get some output. So now if I give you this output, can you decode this back into the original face image which generated this output? So that is the kind of attack which we are talking about here. And if you know about machine learning, this kind of setting is similar to an autoencoder, right? So here you have some data, you encode it into some kind of latent space, and then you're decoding it back to the original space. So the main difference between an autoencoder and a model inversion attack is how the system is trained. So in an autoencoder, you train this encoder and decoder in an end-to-end fashion. So you have the inputs, you pass it to the encoder, get the embedding, and then you do the decoding, and then look at the loss function and then minimize the whole thing together. Whereas here in a model inversion attack, it's slightly different in the sense that your encoder is already pre-trained and you're given a pre-trained encoder and you have no idea about what is inside the encoder. So you can just query this encoder, get its output, and based on the input and output relationship of this encoder, can you reconstruct back the original image by building a decoder. So that is what this model inversion attack talks about. Right? And then the last kind of attack is what is known as model extraction attack. So as I mentioned, so this machine learning service is becoming very popular, and many companies are investing in building these large machine learning models by putting in a lot of data, training effort, and so on. And then they are offering this as a service to users. So users can query this system and get results from the system. But what if by just using this query process, I am able to steal the entire model of the service provider, right? So then that actually destroys the whole machine learning as a service paradigm. So, and then this attack is very similar to another process which is well known in machine learning called as knowledge distillation. So what does knowledge distillation do? So you have some training data and you have what is known as a teacher network, which you have already trained. Usually this is a very large network. And what you want to do is come up with a student network which kind of mimics the teacher network. mimics the functionality of the teacher network. And the way they do it is, instead of training it on the data and original labels, what they do is they take the training data, pass it to the teacher, get some soft labels or the predictions of this teacher model, and then use these soft labels along with the original training data to train the student model. So in this case, the student model can be really small compared to the original teacher model, but it closely follows the predictions of the teacher model. So this is a knowledge distillation approach, which Professor Hinton and his colleagues proposed like 7 8 years back, right? And this is very popular in many machine learning systems. It turns out that by just tweaking this attack, by tweaking this model, this entire knowledge distillation model, you can create an attack. So um, instead of training the student network on the original training data and the soft labels of the teacher, what you can do is I can completely remove the dependency on the training data. So let's say you have a training data and you have already pre-trained a teacher model on that. So in this case, it's called as a target or the victim model. Now I want to generate a student model, or in this case called as an attack model, which, so I have no idea about what is the training data and how the teacher model was trained. All I know is I can generate some queries to the teacher model. The teacher model will make some outputs, and I can take this query plus the output of the teacher model to build a student model, which is called as attack model in this case, that closely mimics the teacher model. So these two ideas are very similar: knowledge distillation and model extraction. The only difference is in model extraction attack, essentially you don't need the training data. All you need is a black box teacher model or the victim model, and then an ability to query this model. So once you are able to submit queries to this model, get the soft labels, and using these soft labels, you can train an attack model which closely mimics your target or the victim model. So this, as I mentioned, affects the whole machine learning as a service paradigm. So these are some of the attacks on machine learning systems. And this paper, this recent paper by Liu et al., it clearly summarizes some of these attacks. And I just put this image from this paper. So there are various possible attacks. And then you have this whole deep learning or machine learning life cycle. And then there are various types of defense for these kind of attacks. So today in my talk, I will focus mainly on this part, the homomorphic encryption part, which is how you use cryptographic techniques to improve the privacy of your data when you are doing training or inferencing. So that is what is going to be the focus of the rest of my presentation. Okay, so now I'll focus on this topic. So what is the need for learning on this encrypted data? How are you going to use this homomorphic encryption in order to improve the security and privacy of the system? So we have already seen that business user has the data, but he does not have the skills or the computing resources to build a model. And he has to share this data with a learning service provider. But in many cases, the data cannot be shared due to legal issues, compliance issues, privacy reasons, and so on. So this is very common in banks, hospitals, and organizations like that. Right? They have a lot of data about patients, about customers, but they cannot, they don't have the expertise to build the model, and they cannot outsource the data to somebody else to build the model for them. So in these kind of examples, it would be really good if you can encrypt the data and send it to the learning service provider. And a learning service provider operates completely on the encrypted data and then gives you the result in an encrypted form. So that is what learning on encrypted data really means. So the question is, so there are cryptographic algorithms called secure multi-party computation and fully homomorphic encryption, which enable you to do these kind of things. But the challenge is they are still far from practically feasible, in the sense that today, if you want to do some operation, let's say you want to do a multiplication on two numbers, you can do it in microseconds probably. But if you want to do the same multiplication in the encrypted domain, so if you want to encrypt two numbers and multiply them in the encrypted domain, then that's going to take orders of magnitude larger time. So usually 3 to 4 orders of magnitude larger time because of the way these algorithms work. and that's why they are still far from practically feasible. So today, many of the machine learning models, if you take hours or days to train them, then you probably need months or years to train them if you want to do it on encrypted data. So the goal here is, can we enable end-to-end machine learning, so which includes both training and inferencing over encrypted data, and we want to do it in a completely non-interactive fashion. So what do I mean by non-interaction, right? So there are some algorithms which say, okay, I have the data, so I do some processing on the data, send it to the learning service provider. The learning service provider will not do the entire computation, but it will do some parts of the computation, return me back some intermediate results. So then I can modify this intermediate results, send it back to the service provider, and they will continue the processing from then on, right? And this way, there's a lot of interaction between the user and the service provider. And if we are able to, this significantly increases the communication cost between the two entities. But if you are able to do that, then you can do things much faster. But the goal here, what we want to do is, we want to avoid all this interaction. So you just encrypt the data, send it to the server. The server, I want the server to learn the model and send me back the model. Or if I'm using it for inference, I just send the encrypted data. The server just provides me an encrypted inference result. So what is this homomorphic encryption? So the inventors of this technology, they came up with this following analogy, right? So you have, let's say you have a person called Alice. She wants to assemble some of the raw materials into a jewelry, but Alice is worried about the theft of these raw materials. So how can the workers process the raw materials without having access to them? So the solution which they came up is what they known as a locked glove box. So what happens really is, this homomorphic encryption is like a kind of a box where you put this ingredients inside and then lock it, right? And but then what you provide is a glove which helps you to put your hand inside this box. So these workers can come, do things inside the box, but they cannot take anything out, right? So whatever assembly things they want to do, they will do inside the box. And then once they are done, they remove their hand, and then Alice unlocks the box to get the result. So this is the similar analogy which is going on in homomorphic encryption. What you're doing is, you want to do some operations on the data. You kind of encrypt the data, which is like putting it inside a box. But then this encryption is kind of special in the sense that it provides you a glove. So you can put your hand inside the glove and then make some changes to the data within that encryption box. And once you are done, you can unlock the box to get the results of the operations which you did. So more mathematically, so this is what really happens. So let's say I have two data points, x1 and x2. I want to do some operation on them. And then let's say y is equal to x1 star x2, right? This is some operation star. And the idea is, can I do an encryption of these x1 and x2, which will give me c1 and c2? Can I do a different or possibly the same operation between c1 and c2, and I get some result d? And the goal is, when I decrypt this result D, which will give me the Y which I want. Right? So instead of doing operations in the plain text space, now you want to encrypt the input data and then do operations on the ciphertext space. Right? And there are many examples of these kind of homomorphic encryption schemes. So the well-known reverse Shamir-Adderman algorithm, RSA algorithm, is the kind of homomorphic scheme, in the sense that the encryption is, you have an input X, you raise it to the power E, and then you do modulus over N, right? So that is your encryption process. And if this is your encryption process, so let's say I have two different messages, X1 and X2. So I'm raising X1 to the power E and X2 to the power E. Raised to the power E. We call that as homomorphic to multiplication operation. And then there are similar kind of crypto systems which are known in the cryptographic community for almost 20, 30, almost 30 years now, right? For example, you have this Goldwas and Mitali system. So this works for bits. So if you have two bits, I can do an XOR operation between these two bits in the encrypted space. But really, the breakthrough in this domain came around 12 years back in 2008 and 2009 by a researcher called Craig Gentry, who was working at IBM. So he came up with this concept called fully homomorphic encryption. So these previous methods, they can do only a single operation. So you can do multiplication, you can do XOR, and then there are some crypto systems you can do addition. But what if I want to compute some random arbitrary function, right? So then I need what is known as a fully homomorphic encryption. So the idea here is I generate some keys, I encrypt some messages using these keys, right? I define the encryption and decryption function, and then I also define what is known as an eval function. And this eval function does not require the secret key; it just requires the public key. And then you define the function and the inputs to this function. And this eval function can actually compute the encrypted value of f of m1 to mt. So m1 to mt are the inputs to the function f, and then f is the value of the function at these input points, right? So if you want to compute this, you can compute directly by using the ciphertext C1 to CT. So that is what this fully homomorphic encryption enabled. So ideally, it should work for any well-defined function, but currently it works both for addition and multiplication. And since any low-degree polynomial can be represented as addition and multiplication, it also can do low-degree polynomial evaluation. Of course, it can do for other functions, but it is not very efficient. So only for this kind of addition and multiplication operations, it is reasonably efficient. And there are some problems in this kind of scheme. So here I'm providing a very simple construction, right? So let's say I want to do some operations on the bits m, which is 0 and 1, right? So the way I encrypt them is use some function like this. So I take some odd number p, a large q value, right? And then I compute p times q. So basically p times q is a multiple of p. And I add something to this multiple of p, right? So this thing is basically called as a noise within the homomorphic crypto system. So actually this noise contains a message. So you have the message m plus 2 times some random number r. So this is what I put in as ciphertext. So you can imagine, right? Given some value m, I basically keep a large Q, compute the multiple of P, right? So compute P times Q, and near that P times Q, I just do a simple modification of it so that it becomes a ciphertext. So it can be shown that it's easy to decrypt it. So you just need to compute C mod P mod 2. So this where mod represents the modulus operation. So the C mod P will remove the P times Q. So you get M plus 2R. And then if you take mod 2 over it, then the R goes away. So you get the M. Right, so it's very easy to see the decryption process, how the decryption process works. And in this case, the public key is many encryptions of the value 0. So I will not go into the details. Basically, security can be established using the approximate BCD problem. Right? So I will not go into these details, but I want to emphasize this point. Right. So now, how does this scheme achieve these homomorphic properties? So let's say I have two ciphertexts C1 and C2. Right, the C1 is given by M1 plus 2 times R1 plus Q1 times P, and then C2 is given by M2 plus 2 R2 plus Q2 times P. So if I add them, what really happens is the noise adds up, right? So you have another multiple of P, which is Q1 plus Q2 times P, plus some noise, where this noise is actually M1 plus M2 plus 2 times R1 plus R2, right? So still, if you apply the decryption mechanism, you should still be able to get M1 plus M2 out of this. Similarly, we can show that when you multiply these two ciphertexts, you get M1 plus 2R1 times M2 plus 2R2. Okay, and then some multiple of P. And again, you can use the same decryption mechanism to get the output values. But the issue here is every time you do an addition or a multiplication, this noise value is increasing, right? The noise value here, I mean, this M plus 2 times R kind of message, right? So that value is increasing. And once this value becomes close enough to P over 4, right? So in that case, if you try to do the decryption, it will start failing. So what this implies is that you can do only limited number of operations using this kind of mechanism. So if you keep on multiplying, let's say different ciphertexts, right? Beyond a point, the noise will grow so big that you'll no longer be able to decrypt. So, and that is called as the depth of operations. So you can do only limited number of sequential computations on the same ciphertext. So that is one of the limitations of homomorphic encryption. And the beauty of the Craig Gentry scheme is that they also came up with a solution to this problem, which is called a bootstrapping or decryption. So I will not go into all the details, but the basic idea is they use a hint about the secret key within the public key itself, and then using some post-processing steps, they can make some changes to the ciphertext so that the noise level actually reduces. And what is the use of this mechanism? So by repeatedly applying bootstrapping, you can improve the available depth. So you can do more computations with the same ciphertext. But the limitation is that it is a very expensive operation. So you want to minimize it as little as possible. For example, even on the most powerful computers, a single bootstrapping step can take a few seconds. So imagine you are doing large machine learning computations, and if you are trying to apply this kind of method, it's going to take forever in order to do these computations. Okay, so then we have these more advanced schemes such as the Ckks method. So most of the homomorphic encryption schemes are defined for integer values because they all work in some finite field. So you have to represent everything as some integer in that finite field so that the operations work. But then this is one of the first schemes that try to work with floating point numbers, or at least fixed point, in the sense that you have fixed number of decimal places after fixed number of um, digits after the decimal places. And this scheme is one of the schemes which proposed how to work with floating point numbers. But the problem is, instead of doing exact multiplication, you start doing approximate multiplication, right? So for example, if I take 1.23 and multiply by 4.56, I get this number 5.6088. So if my input has only 2 digits after the decimal point, here the output will have 4 digits. And then when you do the next multiplication, you'll have 8 digits. And then the next one will give you 16 digits after the decimal point. But then what this scheme does is approximate multiplication. So basically every time there's a round off, I mean, it's not even a round off, you randomly push it to only 2 digits, right? So what really happens is you have some approximate computations. So in these kind of simple things, simple multiplications, this approximation looks very good and very reasonable. But what really happens is if you keep on doing this, applying this method, the precision keeps reducing, and the more computations you do, the more precision you lose. So in particular, every multiplication reduces the precision, and precision decreases linearly with the number of sequential computations. So how does this impact? Let's say I want to use this kind of algorithm for machine learning, right? So typically, machine learning a training algorithm can be expressed as a optimization problem, right? So when I try to do an optimization, so I start at some point and then I apply a stochastic gradient descent and then try to find the minimum value of that function, loss function, right? So usually in practical machine learning problems, the surface is not very smooth. So that's one of the challenges. But let's suppose that there's a convex optimization problem. So you have a very smooth surface and you can easily find the minimum. So in this case, if you start losing your precision, then the surface becomes something like this. So even with some moderate noise, you might be able to make some tweaks to the algorithm to make it converge to the minimum point. Whereas if you have really high noise, I mean, in the sense that if you are doing large number of computations, then the surface becomes really cluttered, right? You have this kind of waves kind of thing, and then you get stuck in the local minimum. It never converges to the global minimum. So this is even for if you start with a convex optimization problem. Imagine if you have a practical machine learning system where the optimization is already non-convex and it's very complicated. And on top of that, if you lose precision, you are never likely to converge to any good parameter values. Okay, so I assume most of you are aware of um, the key recipe for machine learning or deep learning. So you have some training data, you define some decision function or loss function, and basically your goal is to find parameters that minimize the loss function, right? And the way you do it is typically using some kind of stochastic gradient descent. You take some small steps opposite to the gradient and keep updating the parameters. The reason I want to put this is because understanding this is very important. So this is highly iterative process, right? So every time you start with some parameter and then keep on changing the parameter in small steps until you reach the minimum value, right? So this is a highly iterative process. And this here I'm showed a simple neural network with some kind of input, a multi-layer perceptron with an input, some hidden layer, some sigmoid activation layer, and then you have defined a loss function, which is in this case I will define a quadratic loss function. And here the key point here is these kind of deep learning networks work only because of these nonlinear activation. So the two things here is you need larger depth. So here I have just shown one hidden layer, but research has shown that the deeper you go, the deeper your network is, you have more expressive power, so you get more accurate results. So you want deeper network. And then in each layer, you have these kind of activation functions which are non-linear. So I showed you the sigmoid activation, but then there are other activation functions like tan edge value, soft value, and so on. So the key thing here to note is that basically you have these nonlinear activation functions and you have these deep networks. And the third thing is for training, you need the iterative stochastic gradient descent process, right? So there are three main challenges here. So when you want to do things in the encrypted domain, first thing is you cannot do any nonlinear operations. So essentially you have to come up with some kind of an iterative algorithm or a polynomial approximation so that you can even do these computations. For example, if I have a sigmoid, I need to come up with a polynomial approximation of the sigmoid function so that you can compute this value of the sigmoid operation by just doing additions and multiplications. Or in the case of values, so let's say I want to compute the max of two values, I can either compute the polynomial approximation or come up with some iterative algorithms which are listed here, right? So if max can be represented as this function, a plus b by 2 plus square root of a minus b by 2, a minus b the whole square divided by 2. And then you can come up with the iterative algorithm for square root, and using that you can compute the max function. And similarly, if you want to do softmax and things like that, again, you need to come up with Taylor series expansion, and then you need to compute inverses and so on. So you need to come up with these iterative algorithms to do all these nonlinear operations. So essentially, this machine learning model, especially on the training part, it thrives on sequential computations. And we know that deeper networks and nonlinear activations are fundamental to success. And the more epochs you train, usually your results get better. So you need more phases in learning through gradient descent and backpropagation, right? So essentially, it's basic machine learning training is a sequence of computations, right? A large sequence of computations. On the other hand, the FHE in the FHE space, in the encrypted space, sequential processing, we saw that it erodes the numerical precision, and it also, beyond a point, you have to do this expensive bootstrapping operation, right? And as I mentioned before, this noise which is introduced, or like this precision which you lose, is not kind of deterministic. It's kind of non-stochastic noise. So what really happens is you get a lot of false gradient signals, and it's very difficult to do SGD like learning in this kind of setup. So I just want to summarize the barriers which exist now, right? So ideally, if you want to solve a typical machine learning problem, let's say an ImageNet part of problem, you need large depth of computations. So basically, you need a deep network, and then you need to train this network with multiple nonlinear activations and computations, and then you have large number of batches and epochs, right? So you need large computational depth. And then you also need very good computational precision in order of 10 power minus 3, minus 4, and so on. And usually these networks have large number of parameters in the order of millions. So this when you are trying to do this, implement this in the encrypted domain, essentially you are restricting yourself to a smaller depth of computation, typically in the order of few tens, maximum 100 or something like that. And then with limited precision, let's say up to 2 decimal points. Okay, so you're essentially restricting yourself to this box, which is shown here. Of course, the number of parameters is usually not an issue. So because of this reason, because of this FHE barrier which exists, so because you cannot do very high precision, and you cannot do large depth of computation, you are restricted with the barrier. And that's why most of the state-of-the-art networks, they try to um, do very small problems. So single layer neural network or a logistic regression kind of model, that's the best you can do with the state-of-the-art um, um, encryption schemes. Of course, this applies only for training. If you want to do inferencing, you can do larger networks, but essentially inferencing, like, you don't have a sequential steps, right? So you just have to pass through the network once. So if you have 100 layers maximum, you can have like 100 sequential computations. So that is easily doable. So inferencing is not a big issue, although there are some other things which you need to take care of. But inferencing is kind of I mean, it's easier to do compared to if you want to do training in encrypted domain. And the question is, how do we overcome this barrier? And that's where our research is, we are working on coming up with these new input representations that reduce the precision requirement. We are also looking at novel network architectures to reduce the depth requirement, and some efficient training algorithms. Basically, can we somehow avoid these sequential computations involved in a SUD kind of procedure? So that will reduce both the depth and the precision requirements. And finally, we're also looking at better FHE constructions which have um, more depth and more precision, right? So, but that is more from the cryptographic side. So the other three, 1, 2, and 3 are from basically machine learning side. So we are trying to come up with new representations, new architectures, and new training algorithms to reduce these requirements. So these are some of the examples of state-of-the-art in encrypted learning. So most of the works, they focus on the inferencing problem because that's easier thing to do. This includes Microsoft, MIT, and so on. Right? And so many of these existing platforms like TensorFlow, Microsoft Seal, and Facebook, they come up with the script 10 plus PyTorch kind of mechanism. And then Intel also came up with the Berkeley transformer. So all these things, they claim that they can allow encrypted training. But I mean, if you try to work with these tools, you find that there is little evidence that training can be done within any realistic time. I mean, it might be possible, but it will take years for some training to complete. In terms of inference, as I mentioned, CryptoNets showed that Microsoft showed that it's possible to do this inference in the encrypted domain without losing much accuracy. They showed it on the MNIST dataset, and they can do fairly large number of computations, up to 60,000 computations per hour on a single PC. And then this Gessel approach from MIT, they try to improve it. The idea is, as I mentioned earlier, they came up with an interactive protocol where some of the computations, especially the nonlinear computations, are outsourced back to the user, right? So the server is just doing the linear computations, basically additions and multiplications, and all the nonlinear operations are outsourced back to the user. So by using this interactive protocol, they show that you can achieve 3 orders of magnitude faster than computation in CryptoNets. And in terms of training, there are a few methods, but all of them, as I mentioned, they just try to build simple logistic regression model with 100 or 1,000 samples with tens of features. I mean, this is nowhere near what is required for modern deep learning kind of training processes. And in our earlier work in CVPR 2019, we tried to push this boundary by trying to at least learn a simple 3-layer perceptron But the problem is you need to compress, as I will show later, you need to compress the input. You need to play around with a lot of things in order to uh, make it even feasible, right? So even in that case, even with all the optimizations, a single mini batch with 60 samples took approximately 14 minutes to run after parallelizing across 30 CPUs. So you can imagine how slow it is. So as I mentioned, the CATR paper, we basically talked about how do you represent the inputs. Basically, you have 8-bit signed integers to represent the inputs. So this one doesn't use the floating point scheme. It uses an integer-based scheme. Right. So basically, what we found out is the inputs and the outputs of the activation layer, they can be 8-bit representations, but some of the weights need to be like 16-bit representations for the scheme to work. Okay, and so this is a simple network which we tried, as I mentioned, 3-layer network, right? And we use simple functions such as sigmoid activation, quadratic loss, because that simplifies a lot of things. So once you are able to, the advantage of the sigmoid function is the derivative is basically f times 1 minus f. And then for the quadratic loss, again, it's linear. The derivative is linear. So you don't have complex functions when doing the back propagation stage. And what we did is took this homogeneous data set and then process these samples. And one of the real benefits of this scheme is that we really show that you can just work completely with integers and still do some machine learning training. So there's a lot of work in the literature which claims that, oh, we can do it with 6-bit floating point or 4-bit floating point, or I can um, use binary weights, ternary weights, and so on, right? Where you don't need floating point numbers for the weights. But actually, it turns out that when you are doing a training, all these methods, they do some of the computations in the full floating point and then do the truncation. Whereas in this case, we don't have the luxury of switching back between floating point and integers and so on. So we have to fix a representation and then follow that representation. So one of the key results from the study is that by simply um, designing the weights and how you use the bits in the weights carefully, we can do neural network training completely in the integer domain. So that is one of the key results of this paper. But as I mentioned, even for a very small network, so you basically have 64 inputs, 32 neurons and 16 and 10 neurons in 3 layers, right? So this is a very small network in terms of modern deep learning. So if you are doing it in a simple PC, you can do it in a lot of milliseconds, this whole, or few seconds. You can complete the whole training in a few seconds. Whereas what we found is when you are doing in the encrypted domain, even after all the optimizations, it takes roughly around 40 minutes to complete 1 minute batch. So it's that slow. So there is a lot of work to do in order to make it much faster and more realistic. So I'll just briefly talk about this other issue of secure collaborative AI. The goal is basically many of these, in many machine learning problems, all the data is not available with one entity. So let's say if banks want to learn a fraud detection model, each bank has data only from its own customers, but then customers do transactions across banks. So if you want to build a real fraud detection model, then you need to access data from other banks. And similarly, in the case of supply chain scenarios, we have the same kind of issues. So each entity in the supply chain has only one layer of visibility, right? So they know what they ordered with the previous partner in the chain and then what they are going to deliver to the next layer in the chain. Whereas if you want to do real optimization of the supply chain, you need to know what happens in the whole chain, right? And then nobody is willing to give out data regarding all their operations. You cannot pull all the data into one point and then do this machine learning models. So that's where we need this collaborative AI scheme, and which is completely decentralized. So there are federated learning schemes which have been proposed in the literature, which are more centralized or sometimes even distributed, but all of them involve some centralized server that you have to do some local computations, send some information to the server, which will aggregate that information and send back to you. So you have to kind of trust the server at least a little bit. So what we really want to do is completely decentralize this process. So if I have, let's say, 3 or 4 hospitals or multiple banks, and they have their own data, I want them to learn a machine learning model without engaging any central trusted party. So the question is, how do you do that in a very decentralized fashion? And when you do complete decentralization, there is a problem, because in most of the federated learning algorithms, the assumption is all these parties are contributing equally. I mean, they are all playing honest, participating honestly. So they are providing their they're computing their, doing their local computations honestly, and then providing their inputs, which can be aggregated. The question is, what if one of these parties is dishonest? Right? So basically, they are not doing anything, and they want to get the model, or they want to purposely poison the data so that no model gets learned during this process. So you need to take care of these malicious scenarios. That's where we came up with this solution, where we call, which is based on, which is called as fair and privacy deserving learning, where we try to come up with some local credibility metrics. So how do we do that? Basically, each party, instead of sending their original data, they build what is known as a GAN kind of structure, a generative adversarial network, to generate some synthetic data, right? And then basically they send out the synthetic data and let the other parties do predictions on this synthetic data, and you get the results of that prediction, right? So that will help you understand what is the capability of the other participants. So whether the other participants indeed have some data, and then they are able to build some model, and then they're able to contribute to the learning process. And this is similar to, let's say, a group project, right? Let's say in a course, where you have 3 or 4 individuals working in a group, working on the same project. You will have some individuals who contribute more and some individuals who contribute less. But eventually, we don't want everybody to get the same grade. So we want to grade them based on their individual contributions. So that is what we are trying to achieve here. So essentially, by using this GAN kind of approach, generating the synthetic data and forcing the other parties to make predictions on this data, we are able to get some assessment of their credibility. And then we keep on continuously evaluating the credibility as the process goes on. Right? So eventually, in the end, um, the idea is, if somebody has more credibility, they actually also get more benefits from this learning process. So that's how we make the system fair. Okay, so basically, let me summarize what I have talked about today. So AI is far from being a solved problem, and most of the best AI minds are still focusing on a pure AI problem. So given some data and you want to make some predictions, classification, how do you do it in the most accurate way? But as more and more AI systems get deployed in the real world, there is an urgent need to pay attention to issues such as security, privacy, and trustworthiness. So one of the things which I didn't talk about today is explainable AI, but that appears to be one of the key things which tie all these problems together, right? Intuitively, this explainable model. So once you're able to explain how this model is working, then it turns out that they are more robust to many of these attacks, adversarial attacks, and they are also more generalizable. But then often explainability comes at the cost of accuracy. And so when you try to make the model more explainable, you have to simplify it, and then this comes at the cost of accuracy. So how do you balance the trade-off between this complexity and explainability? Seems to be one of the fundamental challenges in addressing many of these security issues. And if you see, all these model inversion, membership, inference attacks, and all these things are also because the model is overfitting on the training data. That is why, by looking at the model, we are able to make some guesses about the training data, or it leaks a lot of information about training data. And by making this model more explainable and generalizable, we can actually prevent many of these attacks. And so basically, I want to just give a snapshot of my research. Today, I mainly talked about this problem of learning on encrypted data, but I'm also working on other issues such as presentation attack protection, which is a spoof kind of problem. Then I'm working on this robust federated learning and privacy preserving federated learning, which are related to model poisoning and things like that. And then a little bit on explainable AI and adversarial attack detection and defense mechanisms, and also fairness in machine learning. So these are some of the key topics which I'm working on in general. So if you have any questions or if you like to discuss with me for some collaboration, I'll be happy to talk to you. Thank you for listening, and now I'll be able to take questions.
Thank you, Dr. Karthik, for such a nice presentation. So we have some typed questions in Q&A box, and otherwise we can also take questions from the audience. So the first question is, as a new approach and till date under progress, do you believe that AI applications are safe and secure for public use, not only by leading organizations like Google?
I mean, my assertion is like even leading organizations and Google, they don't have a system safe and secure. They are still vulnerable to many of these attacks. I mean, actually, many of these attacks they came from Google Labs, right? So Google Research. They're basically trying to. They are the ones who invent the model, and then they are the ones who come up with the attacks on these models. And they are also leading the defense mechanisms. But I don't think um, even Google or Facebook or many of these big organizations will have proper solutions to address all the security and privacy issues.
Perfect. Okay, so another question is, what are the most required educational tools in your opinion to build trustworthy AI systems?
I think the key thing in building trustworthy AI systems is to understand the fundamentals, right? So essentially, we need to go back to the basics. When we say deep learning, we need to say why we need this level of depth and why we need these huge networks to solve this problem. You need to go back to the basics and try to come up with simpler solutions to solve the problem. That is the key point which I want to emphasize. So far, people have been running in one direction, saying accuracy is the most important thing, and then they try to build bigger and bigger models and deeper models to solve the accuracy issue. But then eventually, when you want to deploy that system, accuracy is not the only thing. Somebody can easily come up with other mechanisms to circumvent the system. So the key thing is to go back to the basics and see why we need these big systems and how we can um, build things starting from scratch.
Perfect. Okay, so one question is from my side. In one of the slides, you mentioned that the UAP, Universal Adversarial Perturbations, you generated for medical images were very successful in terms of fooling rate. So did you also observe some common pattern between that UAP and the UAP generated for natural images?
I think they're very similar. I mean, I've not seen, that is not my paper, but
Hmm.
I read the paper and then they say that basically the idea is very similar. It's essentially, they follow the same deep fool kind of model which came in CVP at 2017.
So does it also suggest that like you have a very universal kind of perturbation,
Yeah, I mean
space? Yeah.
that's what the paper emphasizes. Right, the next
Hmm.
paper which I talked about, it's actually not dependent on the imaging type. So it
Hmm.
works across different types of medical images, and
Hmm.
as it works across different types of medical images, it is also likely to work across natural images.
Okay, great. Thank you. So any other questions? You can mute yourself and just ask. So I think that's it basically. Uh, Okay, so I think that's it basically. So thank you very much once again, Dr. Karthik, for a nice presentation, and thank
Uh,
you everyone for joining.
Professor,
Yes, please. Yeah.
Professor, I want to ask, what are the drawbacks of additive homomorphic encryption rather than full?
Okay, so in additive, you can do additional homomorphic space, right? I mean, in any machine learning system, we cannot do all the operations just using addition. You need the full capability of doing multiplications. I mean, even multiplications, additions are not enough. You need to be able to do non-linear operations, which are very challenging. So if you have just an additive homomorphic scheme, uh, it's very difficult to do practical computations using that.
But it's faster, right? Obviously it will be faster.
Yeah, it's faster, but it doesn't solve the doesn't satisfy your requirements, right? You want to do nonlinear computations, and if you just do additive homomorphic encryption, that's not enough.
And Professor, what are the most common or best approach for not having one party generating the private key for the encryption?
In what kind of scenario are you talking about?
In a multi-party learning scenario without a centralized party, there would have to be someone generating the private key for an encryption.
Okay, so there are two approaches, right? So one is we have a multi-party version of homomorphic encryption, where the parties can generate um, keys locally. So you don't have a central server which is providing keys to everybody, right? So that is possible. But the issue with that approach is essentially decryption becomes a sequential problem again, right? So you cannot decrypt in one step. So everybody, so let's say I have an output which is encrypted. It needs to be passed along to different parties, and each party has to apply their key in order to decrypt it. So that is one of the problems with um, multi-party homomorphic encryption. But there are other approaches in the secure multi-party computation literature which are able to do it. And so there, again, there are algorithms which does not require centralized key generation or at least centralized secret generation. So in multi-party computation, you don't need actually keys. You need to but you need to generate some random seeds, and this has to be done locally. And there are algorithms which can do that without any centralized coordination.
Thank you, Professor. Thanks.
Okay, maybe I think then let's thank once again Dr. Karthik, and thank you very much all for joining. So this is basically the end of the seminar. Thank you once again.
Thank you.